The universe is full of wonders. We see stars, galaxies, and vast clouds of gas and dust. But some things are hidden from our view. They are the darkest, most mysterious objects we have ever imagined. We call them black holes. They are places where gravity is so strong that nothing, not even light, can escape. Imagine a star many times more massive than our sun. At the end of its life, it collapses under its own weight. All of its matter is crushed into an incredibly small space. This creates a gravitational pull so immense that it warps space and time around it. That is a black hole. For a long time, black holes were just an idea. They were a prediction of Albert Einstein's theory of general relativity. But now we know they are real. We have seen the effects they have on nearby stars and gas. We have even taken a picture of the shadow of a black hole. There is a supermassive one at the center of our own galaxy, the Milky Way. It is called Sagittarius, a star. It weighs as much as 4 million suns. On one hand, we have a brilliant theory of gravity. It is called general relativity. On the other hand, we have another brilliant theory. It is called quantum mechanics. General relativity describes a smooth, continuous universe. It tells us that gravity is not a force. It is the curvature of space and time caused by mass and energy. Quantum mechanics describes a lumpy, quantized universe. It is a world of probabilities and uncertainty, but it is also incredibly successful. Here is the problem. These two great theories do not work together. When you try to use both theories to describe the same thing, you get nonsense. But there is one place where both are needed. That place is a black hole. This brings us to the ultimate question in physics. How do we unite these two theories? We call this undiscovered theory quantum gravity. Finding it is the holy grail of modern science. The event horizon is the black hole's famous point of no return. It is not a physical surface you could touch. It is an invisible boundary in space. Crossing the event horizon would be a surprisingly quiet event. For an astronaut falling through, nothing special would seem to happen at that exact moment. But for us, watching from our spaceship far away, the story would be very different. We would see our astronaut's clock ticking slower and slower as they approach the horizon. If we could follow our brave astronaut past the event horizon, their journey would become increasingly violent. The destination is the black hole's center. It is called the singularity. According to general relativity, this is the true heart of the mystery. It is a point of unimaginable and indeed infinite density. At the singularity, the curvature of space-time becomes infinite. The pull of gravity becomes infinite. Time and space are no longer a smooth fabric, they are torn apart. Outside the event horizon, physics works perfectly. We can navigate spacecraft, build computers, and understand the life of stars. But inside the event horizon, our two greatest theories are locked in a conflict they just can't resolve. The singularity is the ultimate impasse. The singularity forces us to confront this deep and honestly unresolved paradox. This is why black holes are not just astronomical objects, they're theoretical laboratories. One of the most famous ideas for quantum gravity is string theory. It suggests that fundamental particles are not points, but tiny vibrating loops of energy. Another leading contender is loop quantum gravity. It suggests that space is not a smooth sheet, but a network, a woven fabric made of finite loops. These are not easy ideas to test. The energy levels required are astronomical, far beyond anything we could build on Earth. This is why black holes are so essential. In 2015, everything changed. For the first time, humanity detected gravitational waves, ripples in the very fabric of space-time. It was the sound of two black holes colliding. This cataclysmic event converted an amount of mass equal to 3 of our suns directly into gravitational wave energy. And we heard it. We heard the chirp of space-time itself, ringing like a bell. This was a profound moment for physics. Physicists are looking very closely for any tiny deviations. What if the ring-down signal contains faint echoes? Such echoes are not predicted by standard general relativity. Their existence would suggest that the event horizon is not the simple one-way door that Einstein described. It might mean there is some new physics at play right at the edge of the black hole. Finding these echoes would be the first ever experimental evidence that points towards a specific quantum structure at the event horizon. In 2019, the Event Horizon Telescope collaboration released the first ever image of a black hole. It was not a single telescope, but a network scattered across the globe. The image shows the bright ring of hot gas swirling around the event horizon. At the center is a dark circle, the shadow of the black hole itself. The size and shape of the shadow match the calculations of general relativity with remarkable precision. It was another great victory for Einstein. But physicists are now scrutinizing this image for tiny details that might disagree with Einstein's theory. Any deviation would be a signpost pointing towards new physics. The Event Horizon Telescope is constantly being upgraded. This will allow us to create sharper images and even movies of the gas swirling around the black hole. The shadow of a black hole has become a new cosmic blackboard where we can look for clues to finally probe the deepest mysteries of black holes. We have journeyed to the very edge of human knowledge. We have stared into the abyss of a black hole, a place where our most successful theories break down. They are the ultimate laboratories, creating extreme conditions we could never replicate on Earth. They are not just the end of a star's life, they represent the beginning of a new chapter. The mystery beyond the event horizon forces us to ask the biggest questions we can conceive. What is space? What is time? What are the ultimate building blocks of the universe? Why does this search matter? The answer goes to the very heart of what it means to be human. We are a curious species, always looking up and wondering about our place in the cosmos. Solving the puzzle of quantum gravity would represent the culmination of a scientific revolution that began with Galileo and Newton. It would be the final unification of physics. We are living in a golden age of black hole astronomy. With our incredible tools, we can now listen to the symphony of colliding black holes and see the shadows they cast. The coming decades promise even more exciting discoveries. We plan to build new observatories that will listen to the faint hum of the gravitational wave background of the universe. Each new observation is a potential clue. We are meticulously assembling a puzzle, hoping that a coherent picture of quantum gravity will emerge from the patterns we uncover. The dark, silent voids of black holes are calling to us, and with our insatiable curiosity and ever-improving tools, we are finally beginning to listen to their secrets. The quest continues.